Okay, let's see. Okay. How much time? You want to know something? We got the time. I want to go over this first example first, just so we cement this a little bit. Total cholesterol values for a certain population are approximately normally distributed with a mean of 200 milligrams per 100 milliliters, I guess, of blood, and a standard deviation of 20 milligrams. Find the probability that an individual picked at random from this population will have a cholesterol level between 180 and 220. Well, I don't even have to draw that, right? 200 milligrams, 200 is the mean, 20 is the standard deviation for the population. In other words, mu and sigma, right? And we're asking what's the probability that a randomly selected person will be between 180 and 220. Well, that's one standard deviation below and one standard deviation above. So the probability they would be in that range is about 68%. Everybody comfortable with that? Right? Yeah. Right? Makes sense? Okay, now we're dealing with the population again now. Okay, what's the probability to be between 160 and 240? Two standard deviations apart, so it's going to be 95% certainty, right? Okay, and what's the probability that they're going to be greater than 225? Uh-oh, we got an issue here now, right? That's a problem. Okay, and the way we're going to take care of that problem is we're going to do a quick calculation. My notebook. Okay, and I'm going to go to my second page here. Oh, I went the wrong direction. Okay, so I like to sketch this out, and if I go over here and sketch this out, the population I just described has a mean of, what did I say, 220? 200, was it 200? 200, that's mu, and sigma is equal to 20, right? And what did I say? I wanted to know what percentage of the population was, what was it, 225. How many standard deviations above the mean is 225? Well, I know we can figure out that score, that z-score. It's equal to x minus mu over sigma, which is going to be equal to 225 minus 220, 200, the mean, over 20, which is going to be equal to 25 over 20. It's a positive number because it's the right side of the mean. Okay, it's going to be equal to 1.25, right? So it's going to be somewhere around here. We want to know what's the probability that, what did the question ask? Probability that it's greater than that? Yeah, what's the probability that we're going to pick somebody up in this area over here? So we need to predict what that area is. And we know that since it's not an even number of standard deviations, integer number of standard deviations, I can't use I can't predict it based on that table, our rule. Okay, so I have to go to the z table. Now on Blackboard, I posted a couple of z tables for you. I'm going to open one up of the group that's on Blackboard. Let me get to my desktop and session 5. Okay, and standard normal distribution. Here's the aggressive one. I like the aggressive one. Okay, now it's a positive 1.25. So notice that the aggressive table always gives us the area to the left of Z. I'm interested in the area to the right of Z because I'm looking for people that are higher than that level. Okay, so I'm going to have to go all the way down here to the positive numbers. See, now we're on the correct side of the mean. Okay, 1.25, 1.2, was 1.2 or 1.25? It's going to be 1.2, 1.20, 1.21, 2, 3, 4, 5. 1.25 is 0.894, or about 89.5%. So, but what is that? What is that telling me? What area is that identifying? That's saying that this area, from here down, is 85, 84.5%, 89.5%. I have no memory. I'm shot. I have no memory. 89.5%, right? So what does that mean? The probability that you pick a random person that's in this area is going to be 10.5%, or the difference between 100% and what the area below it. Okay. Another way to express that would be as a probability was 0.895 and 0.105. Same thing. Right? Okay. So now Let's look at the next one. What's the probability that a randomly selected individual is going to be less than 150? Okay, well, less than 150, well, let's see, 50, let's see where we are here. Let's see, less than 150. So our z-score is going to be equal to 150 minus 200 over 20. How many standard deviations below is that? Well, that's, let's see, that's 50 over 20. So that's going to be 2.5, right, or 2.5. It's going to be a negative 2.5, 150 minus 200. And it's negative because it's to the left of the mean, right? So if I go back to the table, okay, and if I can get to the table again, I have to start to learn like, they change every time they, it seems to me like every time they change the upgrade an operating system on the Mac, they change some of these shortcuts. So I keep losing track of them. Okay, so at any rate, negative 2.5. So that's going to be on the other side of the mean. So you can use the other tables to do this. Use a single table to get the areas that you need, and then take advantage of the fact that the standard normal distribution is symmetrical. So you can take advantage of it. This table actually makes it a little easier for you. So negative 2.5 leaves an area to the left of that of 0.006. Right? So this area, right, that's negative 2.5, can be around there. So the probability of picking someone out that has a cholesterol in this population, whichever population it happens to be, less than 150 is 0.006, or in other words, about 0.6%. Right? Relatively unlikely. But that you expect it to be relatively unlikely because it's so far away from the mean, 2.5 standard deviations away from the mean. The last question we asked, what's the probability of finding someone whose cholesterol is between 190 and 210? And now we're going to do, now it's going to get pretty interesting now. So I'm going to redraw this. So here's our mean is 200, and that's mu. Sigma is equal to 20. So this is 200. So now we're interested in the probability that you would pick out an individual who has a cholesterol between 190, and did I say 210? 210. Okay, so we want to know what percentage of people are in this area here. Well, we don't have a table that measures the middle, right? So actually, to tell you the truth, there are a couple of tables that actually do that. They give you the area from a point to the z-score in the middle. We don't have that. Okay, so how are we going to do this? Well, I'm going to do 210 first. The area to the left of 210, because that's what the table gives me, is going to be, let's see what the z-score is. 210 minus 200 over 20. The z-score is equal to 0.5. Okay, let's see what that area is. Okay, here we go. Okay, plus 0.5. Plus 0.5, that's 69.15%, or 0.6915. So this area to the left here, this area is 0.6915. Well, now, if I know what the area to the left of this is, I can just subtract this area from the larger area, and it's going to leave me this bar in the middle. Let's find what that is. That's going to be negative point. It's 10 below, so I know it's going to be negative 0.5. So I'm not going to bother to do that. I hope I don't confuse you by not doing that. So I'm going to go to negative 0.5, and that is going to be 0.3085. Okay, so this area in here, from here to the left, is 0.3085. So if I subtract one from the other, 0.6915, and subtract 0.3085, it's going to leave the area in here. And answer my question, what's the probability, what's the percentage of the population that's between these two values for this normally distributed population? That's going to be 0, that's going to be 8, that's going to be 3, 8, and 38.3 or 0.3830. straightforward, right? We really kind of did that last week. Let's move on from there and see what we can do next.
You also know that's half the area of the 68, right?
I'm sorry?
You would also know it's half the area.
Oh, no, it is. Stop for a second. It's not. Because if you were talking about, that's an easy mistake to make.
Oh, because I thought that was half it.
Yeah, I know, not, see, look, if you were talking about the area between here, like one standard deviation above, right? You know that's 68%. Now, if you were saying, what's the area between the mean and one standard deviation above, or one standard, those are 34%.
Right, so 34
right? No, what happens here is, if you're half a standard deviation, you're in the high part of the curve. This area is much bigger than the sum of these two areas, right? So you get the idea, because you're not really comparing symmetrical parts. Yeah, you can do that with symmetrical parts, like when you do standard deviation. Divide standard deviation, two standard deviation below, and one standard deviation above, and divide that in half. That's symmetrical, so you can assume the areas are the same. Okay, and let me just check on mine here before we move on to the next one. Okay, not too many, no questions there yet. You guys, they fell asleep. Okay, we're on our own. Okay, so next, let's take a look and let's do our first exercise where we apply our knowledge that we just picked up about sample distributions, about what the behavior of samples. We take a sample of size 25 from the same population we were just talking about. The population has a mean of 200, standard deviation of 20. Normally, you wouldn't know that, right? But we take a sample of size 25 from that sample. What's the probability that the mean of the sample is larger than 204 milligrams per 100 liters? Okay, so now, if I look at this, look now at the distribution of all the samples, of millions of samples of size 25 from that same population, what's this new distribution of sample means going to look like? Well, let's see. It's gonna have approximately the same mean. The mean's going to be the same. In other words, half the time we're going to get a sample below of size 25. We're going to average with a sample below 200. Half the time we get a sample above, right? Stands to reason, because we're taking it from a population with a mean of 200, right? But now the thing that's going to change is, instead of the standard deviation of the population was 20. Now, since we're looking at samples of size 25, the results that we base our new distribution on are going to be much narrower. So the standard deviation for these samples, repeated samples that we took over and over again, that standard deviation we're going to call the standard error instead of the standard deviation. And what's that going to be equal to? Anybody remember what the formula was? Standard deviation in the population over sample size, square root of the sample size. Right? So the standard error is equal to 20 over the square root of 25, which is 5. So that's 20 over 5, and that's equal to 4. So now, these results, if I take repeated samples, they're going to be spread out much less than the actual numbers from the population. So let's see what they ask us about this, and that was things that we can predict. What's the probability that the mean of a sample is larger than 204? So now what we have here is we have something that gives us an idea of how, if we took a sample of size 25, how that's going to behave. What's the likelihood? First of all, what's the likelihood that if we take a sample of 25 in that population, what's the likelihood it's below 200, the result? 50%, right? Because half of it's going to be below 200. Likelihood it's above 25 is going to be 50%. Above 200 is going to be 50% also. But now let's take a look at that specific example. What was that again? Likelihood that it's above 204. Okay, well, let's see. Now I'm going to look over here, and 204. What's the z-score in this new distribution with a standard error of 4, right? What's the z-score that value of 204 would represent? Well, it's going to represent, let's say, 204 minus 200 over the standard deviation for these sample means, which is the standard error, which is 4. So the z-score is equal to 1. right? So if we take a sample of size 25, and it probably means, okay, if we take a sample of size 25 from the population in the previous example, right? The probability that the mean of that sample is going to be greater than 204 is the area here in this new distribution that's specific for samples of size 25. We would have a different distribution for samples of 100, right? Because this standard error, because of the square root of n, is going to be different. So what's the probability? Well, since this is one standard deviation above the mean, we know that this over here is 68 and this is 34 because we knew it was, as you said, symmetrical. So the probability we get a value above 204 is going to be about 16%. 0.16. Okay? See the difference here? We're applying the same rules, except now we're using the standard error to predict what the samples are going to do, rather than using the standard deviation to predict what any individual, where any individual would be. Okay, now let's take the next part of this. Yes. I'm not sure what I said last.
You said the standard error.
We're using the standard error this, in the distribution for the sample means the same way that we use the standard deviation to try and predict what the probability is that we would pick a person that has a value above or below some level. We're using the same rules, we're using the same technique, except now we're substituting standard error for standard deviation because we're dealing with a narrower distribution. So we know the percentage.
So standard error always refers
to the sample means, right? Sample means, exactly right. That's exactly right. Okay, what's the probability that the sample mean is between 192 and 204? Well, 192 is going to be one standard deviation. Oh, I'm sorry, I'm wrong. 192, whoops, it's actually 192 is going to be down here. 192 is two standard deviations to the left of the mean. So this is half of 95%, right? So this is 47.5%, right? And we know this area in here is 34%. So the area between 192 and 204 is 47 plus 34, which is about 81.5%, right? I'm doing the same thing I would have done with the population itself, except I'm using the standard error, that 4, instead of the standard deviation for the population, because the distribution means is not as far apart, and they're narrower. If I had done this for 192 and 204, the percentage, it would have been only caught some of the population, a smaller proportion of the population, because it's more spread out. And it wouldn't have been as high as 81%. Okay, next. If we took repeated samples of size 25 from the population, within what range would we expect 95% of the samples to fall? Very interesting question here. If we took repeated samples of size 25 from the original population, what range would we expect 95% of the results to fall within for those samples of size 25? Well, I'm gonna, since that one's important, I'm gonna take up another piece of paper here. Here's our sample distribution. It's gonna be, we expect it to be, this is 200, and the standard error we know is equal to 4. We got that from the standard deviation over the square root of n, which was the standard deviation of the population is 20 divided by the square root of sample size 25. They told us the sample size is 25. So if we took a sample from that population, if we knew that the population was 200, the mean for the population was 200, and the standard deviation of the population was 25, if I took a sample of size 25 from that population, I could now predict that the sample is I could be 95% certain that the sample is going to fall within 2 standard errors below the mean and 2 standard errors above the mean. And what is that? That's going to be 192 to 208. I'm 95% sure if I take a sample of size 25, that the mean of that sample is going to be between 192 and 208. See how that now allows me to predict and understand how a sample from a population is going to behave by knowing something about the standard deviation of the population. It gives me an understanding of where I would expect it to fall. And if I got a sample, if I took a sample of 25 and it wound up being less than 195, I mean, or more than 208, that would be unusual, right? That would not happen very often, happen less frequently. Okay? So that's the key here. That's why we're learning about standard error, because we want to be able to make predictions about the relationship between a sample, its mean and distribution, compared to the population mean and distribution. Because we sample we know, the population we don't know most of the time. Okay, let's see if we got another question that we can move on to. And each time you do this, each time you work out an example that involves this, it's going to become a little clearer and a little clearer and a little clearer. And one day in the dark at home, sleeping, a light is going to bing, a light in your head is going to go off, and it's really going to, I guarantee it, it's really going to click. In fact, I guarantee you that you can, this is in recording, so you can go back and look at this. When you by the time we get to week 7 or 8, or well, we only have 7 or 8, by the time this is not a real semester with the summer session, by the time we go forward another couple of weeks, you're going to look back at this and you're going to say, oh, that's so obvious. I don't, it makes perfect sense that this is what we're doing with this information. A sample of size 100 is taken from the population above. It's a bigger sample size. So what's going to happen to our understanding of how the sample is going to relate, repeated sample is going to relate to that mean? They're going to be much tighter. They're going to be every value. Every time you take a sample of size 100, it's going to be closer to the mean than a sample of size 25 is, right? Because it's a better estimate of the mean, right? So what range would we expect 95 of the sample means to fall? Okay, well, I'm going to do that now. Let's see. Standard error is going to be equal to, it's going to be equal to 20 sigma over the square root of the sample size, which is 100, square root of 100. That's 20 over 10. So our standard error is going to be equal to 2, right? So now what does that tell us? Well, that tells us that we would expect 95% of the mean, if we took a sample from that population, a sample size of 100, we're 95% certain that the results of that sample would be between, let's see, instead of 192, it's going to be between 196, right? 2 standard deviations below, and 204. It's a much, see, I really, by all rights, I should draw this as a narrower distribution. Same mean, but a narrower distribution. So we're talking 196 to 204. Okay, that's how this works. The bigger the sample size is, the smaller the standard deviation, standard error, the bigger your confidence is about where the mean is, right? Sample size helps you with that. Okay, so, okay, so now let's take a look at another example. You sample 100 bottles of detergent and find that on the average, each bottle will be sufficient for 57 loads. On the average, right? Some of them will do 53, some of them will be 67, some of them will be 61. It's just that, first of all, when you look at these things, you got to filter out all the extraneous information. It doesn't matter that it's bottles of detergent and washing loads. We know the sample size is what? N is what? 100. We sampled 100 bottles. And what's the mean? The mean is 57. You know that the standard deviation for the entire population of bottles is 5 loads per bottle. That's the spread for the entire population. We have a funny combination of information here. We don't have the sample mean here. We don't have the population mean. We have the sample mean. But they happen to tell us, we happen to know or have an educated guess at what the sample standard deviation is. Why is that the case? And why we would usually expect that to be the case? The answer to that is no. The reason why we have it in these examples that we're going to be working up the next day or two the next session or two. The reason why we know it in these examples is because we're simplifying this so we don't have to worry about our uncertainty about the population standard deviation. It's just so that we can do these exercises, basically. Okay, so let's see what we got here. So we have let's see, I can get both of these here at the same time. We have our mean here. First of all, we got a sample size of 100. Okay, so what's our mean? Our mean is how many washes do they get out of each bottle? Again, an average of 57 loads out of each bottle. Now, what should I put here? Should I put mu here? What do you think? Mu? Is mu the right thing to put there? No, probably right. Mu would be the population. We don't know the population. We don't know the average for all 100,000 bottles. We only know the mean for the 100 that we average, right? This is going to be called X bar. X bar means the sample mean instead of the population. We use that simply to distinguish the population mean from the sample mean. What is the sample mean? Do we know the sample mean? No, we don't. We have no idea what the sample mean is. All we know is the mean of the sample that we took is 57. Those 100 bottles is 57. We don't know what the real population means. Now, for some reason, some accident, we know that the standard deviation for the population, sigma, is equal to 5. The spread is, 95% of the time you'll get between 47 and 67, and so on and so forth. That's what sigma represents. Okay, well, or 10 below and 10. 95% of the time you'll get a number of loads that's equal to 10 below the population mean mu and 10 above the population mean. That's what sigma is telling us. Yes. Okay, so let's see what questions they ask us about this. Is 57 mu or X bar? We know that it's X bar. It's the sample mean. And that's called a parameter, not a statistic. A statistic is your sample, anything you get from your sample. A parameter is anything that represents the population. So in this case, it's X bar. Is 5 sigma or SD, standard deviation? Well, we said that's actually the population standard deviation, sigma. That's why I wrote it down as sigma. Calculate the standard error for repeated samples from this population of size 100. That's sigma over the square root of n. So what's the standard error for taking samples of size 100 over and over again? It's going to be equal to sigma, which is 5, over the square root of n, which is 100. 5 over 10. Standard error is equal to 0.5. Okay, so now let's take a look at the next thing they asked us. Calculate the 95% confidence interval for the population mean based on this sample. Oh, well, what are they talking about? Well, the mean came out to be 57. And I know that the standard distribution, the spread, since we know the standard deviation, I know that the spread, if I took samples over and over again, the way that they would be spread out is in a manner where the standard deviation for these samples, or what we call standard error, would be equal to 0.5. So I know in that case, 2 standard deviations below 57 and 2 standard deviations above 57 is going to be equal to, it's going to be equal to 56, 2 times 1/2. It's going to be equal to 58. So that's 95% of the likely outcomes for our repeated samples. In other words, since we know since we got a mean of 57, right, from our sample of size 100, and we know the population standard deviation is 5, combined with our sample size, we know the spread of repeated samples, how the samples are going to behave. So basically, that tells us that even though we got a 57 as our sample, does that mean that that's the population mean, 57? No, we don't know the population. It could be 58, could be 57.5, could be something a little further away from that, a little closer. We don't know what the population mean is. But now we know with 95% certainty, because we know the population standard deviation, and we know the way that standard error behaves, we know that with 95% certainty that the true population mean is between 56 and 58. How is that more valuable than just having a mean, just predicting a mean of 57? If we just give you the number 57, without being able to communicate to you how certain we are about that number has limited value. Oh, Tony, how many loads can you get out of the average bottle from this manufacturer? Oh, 57. Oh, you sure of that? Nah, not really. It could be more, it could be less. Well, how sure are you that it's 57? Well, I can't really tell you, how sure I am. On the other hand, if I could tell you that I'm 95% certain that the true mean for how many loads you can get out of out of the average bottle here is between 56 and 58, that's more valuable because now you've quantified what the error could be. Now you know, yeah, now you know that not what the precise mean is, but you know what range that you have 95% confidence that it lies in. And that has real value to us.